Hello and welcome back to Calculus 1. We are going to continue with section 3.9. Last time the stream exploded, so we're just going to go over the notes and then finish off the section. I started the lecture with refreshing your knowledge on logs, which so what are the logarithms? I show that logarithm is just mathematical operation between two numbers to get the third, like any other operation and it's the inverse of exponential, which is the reason why we have this conversion formula here, which allows us to solve exponential and logarithmic equations. So I said that logarithm over here is the operation between two numbers, in this case 3 and 1 over 9, and it's a little bit unique and special, so we use the conversion to convert this expression into exponential expression, and then we compare the exponents and we get that x is -2, so that means that log base 3 of 1 over 9 is -2. So just like 2 plus 3 is 5, log base 3 of 1 over 9 is -2. We use calculator most of the time to calculate logs. In the past, people used log tables and slide rule and so on. And then I explained about a function. So when you say 2 plus 3 equals to 5, that's not a function, that's calculation. If you replace one of those values with variable x, it becomes a function. At linear function. Then we had another linear function, y equals 2x, or x over 2. So log 2 of 8 is not a function. It is a number. It's 3. But if you replace the 8 with x, it becomes a function, and then you can talk about x and y intercept, domain, range, and everything else that the function has. Now we have the 5 basic formulas or rules for logs. Log of any base of 1 is 0. Log of any base of the same number is 1. Log base 10 has the shorthand notation as just logx. And log base e of x, which is a special number, right, is ln x. And those have the buttons on the calculator. Since your calculator only has log base e and log base 10, we learned the change of base formula to transform any log base into either log base 10 or log base e, and you can use the calculator to compute the values. And I asked you yesterday to learn these formulas because we are going to need those formulas for today, and you can utilize these formulas to learn the most impressive derivative taking technique, which is really powerful, called logarithmic differentiation. Then we proceeded to find the derivative of basic log functions. So ln x was 1 over x, ln f of x was f prime over f, which you will use 99% of the time. And then finally we have the boss of all equations, right? It's a log of any base of any function, which is given by f prime over f times ln of base. So all of these formulas can be proven clearly. These are the shortcut formulas, so you need to remember these. So you don't have to crank the limit. You can just use these. And then we have few examples. So ln of secant x. Note that the secant x was copied in the denominator, and then derivative of secant is secant tangent, which is in the numerator. And it follows the same for all examples. Now, what I mentioned yesterday is that for the first example on top, this 2 can jump in front, and that's how we can immediately get the last result if you use the power formula. And then I wanted to outline the difference between the two examples here by switching the placement of the square to denote that the top part was the function composition. The bottom one is also function composition, but they're quite different. And as you can see, you are getting a very different answer in the end. And this is followed by a few exercises from the textbook that utilize chain rule most of the time. So we know that we can combine the rules. We know that we can work on some really annoying exercises that would take forever. We know that we can combine product rule with chain rule with quotient rule, hopefully not all in the same problem, right? But multiple of those can show up. So how do we deal with that? What do we do when the expression looks absolutely insane? Is the stream okay? Yeah, good. So let's consider, I don't know, d dx. So we're trying to take the derivative of 3x squared plus 1 raised to the 4th power times the cube root of x squared minus 1 divided by x times x plus 6 to the 3, whatever. So how fun is this derivative? What do we have as the features over here? Everything multiple times, right? Yeah. We see that each one except the single x has the chain rule to it. We have a product rule in the numerator, product rule in the denominator, and the whole thing is a quotient rule, right? Now, what if I told you that we can just take the derivative of this mentally? Without writing anything down. If you practice for a bit, you can just look at the problems like this and just say the answer, say the derivative in factored form, without using any of the rules, product rule or chain rule or anything like that.
Rule individually, like say 3x squared plus 1 to the 4th. You know what you can do the chain rule, not.
Well, those little chain rules you'll have to do, but you can just write out the answer for this right from there and technically skip the whole page of work that goes in between. And there is a really cool hack that actually is at work there. And some students decide to really learn this because it's so damn impressive, where you can look at technically any expression and you can, doesn't matter. And the more complicated it is, the more impressive it is that you can actually just look at it and write it down without doing any work. So when you know the rules of logs and you know which procedure works in the background, you will say that the derivative of this is 3x squared plus 1 to the 4th times the cube root of x squared minus 1 divided by x plus 6 to the 3 times, I told you it's already factored, so that would be actually factored out. The original problem factors out. And then inside, you will have 4 times 6x over 3x squared plus 1 plus 1/3 times 2x over x squared minus 1 minus 1 over x and minus 3 over x plus 6. And that's the derivative. That's it. You could simplify now. 4 times 6 is 24. And maybe you can steal this 2 and put it as a 2/3 in front. But other than that, we can't do anything else. So now the goal is to see the mathematics behind this, which is going to take a lot of writing. But then if you catch the pattern, you will be able to differentiate anything just like this, without any of the product rule, chain rule, or so on. So let's see how this works. We are going to actually consider this as a very simple function, and then we're going to build up to something that looks as crazy as the expression we had.
So the last one came from the fact of like log times log is
Yes.
log plus log.
So here we go. Let's say that the function that you want to differentiate is, we'll take something easier. Let's say x squared times the 4th root of x plus 3 divided by x cubed minus x squared plus 1 to the whatever, 3rd power. Doesn't matter. So this is a little bit less crazy. And what we need to do here is, if you want to find the derivative of something like this, you apply ln to both sides. And this is where those formulas, ln xy equals ln x plus ln y, ln x over y equals ln x minus ln y, and ln x to the p is equal to p ln x kick in. You need to expand the right hand side, and you get a whole bunch of easy derivatives to take. So when you expand the right hand side, you get ln y is equal to ln x squared plus ln of the 4th root of x plus 3 plus, minus, because it's in the denominator, right? For division you subtract, minus the ln of x cubed minus x squared plus 1 everything cubed. Now we are going to use the power rule to kick all the exponents out. So I have the ln y is equal to 2 ln x plus 1/4 ln of x plus 3 minus 3 ln of x cubed minus x squared plus 1. So all I did is I used the power rule to kick all of the exponents. And it's at this point when it's very easy to take the derivative, because we know that the derivative for ln functions is just derivative of the function divided by the function itself. So if you're looking at the derivative here, you have 1 over y dy dx. Remember the implicit differentiation, right? The derivative of ln y must be 1 over y, and then follow with the chain dy dx. And the rest is easy. You have 2 over x plus 1/4, copy the function as is and its derivative on top, minus 3 times, copy the function as is and its derivative on top, which is 3x squared minus 2x. If you notice, this y needs to go to the other side, and that's the original function, which is why I rewrote. If you remember, when I did that example mentally, I copied the function exactly. That's because you will always have that 1 over y, and when you move it to the other side, it becomes y times everything else. And the everything else is the string that we have from those number of ln's. So this becomes dy dx is equal to y times 2 over x plus 1 over 4 times x plus 3 minus 3 times 3x squared minus 2x divided by x cubed minus x squared plus 1. And all I need to do is to replace what y is, and the derivative is done. Now, this might look, convoluted and crazy, but it's very systematic if you know how to take these derivatives. Minus x squared plus 1 cubed times 2 over x plus 1 over 4 x plus 3 minus 3x squared minus 2x divided by x cubed minus x squared plus 1. And that's the derivative. Far easier than if you try to work out the product rules, the quotient rules, and all of the other stuff. It is very systematic. So let's take a look at another example. Say y equals x squared plus 1 to the 5th power divided by, say, x cubed times the square root of x cubed minus 8, whatever. So you know the first two steps. ln both sides and expand. So let's go step by step. ln both sides and then expand the right hand side using those basic pre-calculus rules.
Of course, so it's closed.
So now we take the derivative, right? Derivative in respect to x. So 1 over y dy dx is equal to 5, copy the function, derivative on top, minus 3, copy the function, derivative on top, minus 1/2, copy the function, derivative on top. dy dx is equal to y, which is x squared plus 1 to the 5th divided by x cubed times the square root of x cubed minus 8, and then in parentheses we have 10x over x squared plus 1 minus 3 over x minus, you can do 3/2 times x squared over x cubed minus 8, and that's it. 3 lines. That was it. 3 lines to take the derivative, which had 2 chain rules, a product rule, and a quotient all on a pile.
So why I guess we have to learn all that other stuff, but we could just use this all the time, right?
That's true. You can use this 100% of the time. Why not?
I mean, that'd be a pain in the ass if you find the y value for a given x, and you have to plug it in, right?
The other one is worse.
You'd have to do all those other things, even then.
Yeah. You see, if you have, let's consider a problem that you did for product rule, where you were looking for the derivative of x squared sine x, right? If you ln both sides, you come up with ln y is equal to 2 ln x plus ln of sine x, right? And from this point, you have 1 over y dy dx when you take the derivative, and then you have 2 over x plus sine x cosine x, and the problem is solved. Now I know that it's much easier to do the product rule on this, but I'm just showing you that this method works all the time. It doesn't matter how simple or how complicated the problem is, but you definitely don't want to use the basic method that we learned, the product rule and the quotient rule, on the complicated problem that I showed in these examples, because it will take a very long time, and then simplifying in an algebra behind it, it will be 10 times worse. So we have x squared sine x times 2 over x plus cosine x over sine x, and as you distribute, you get the answer. Now, I would agree with you that this is much worse than if you just did the product rule. But this is way too simple of an example to use such a powerful method. The only thing that I'm doing right now is telling you that it can be done. Yes?
I'm not sure, but isn't cosine x over sine x equal to cotangent?
Yeah, but when I'm distribute now, it will cancel. 2x sine x, and when I distribute in the next one, it becomes plus x squared cosine x, which is exactly what you would get if you did the product rule. You would get this.
So where did the 2x come from?
Derivative of the first, copy the second, plus copy the first, derivative of the second.
Didn't you already derivative? You had the 2 things there. You had the thing in the parentheses part.
When I multiply these two, x cancels and it stays as 2x. So I did a very basic problem with the same Now, this method also is the only way that you can use to differentiate certain types of a problem. So, if you have y equal x to the x, the only way to solve this problem is using this method, ln both sides. Or if you have, let's say, y equals x to the tangent x, right? I mean, I believe this is actually in your textbook, one of the homework exercises. So this method is designed to solve these types that nothing else can do. So that you can't use the product rule, quotient rule, chain rule, none of those for these particular problems. Only logarithmic differentiation works. So let's do both of these. I will outline again. We ln both sides, and then one of these x's drops down, and that's how we get x ln x. And now when you hit it with the derivative, you get 1 over y dy dx is equal to, and now you have product rule on this side. So copy the first, derivative of the second, plus copy the second times derivative of the first. And as you can see, we have to use the product rule now. And that's it. Now, I have to show you this so you guys can understand that it's not just, you know, pass the class, or, you know, this particular thing in Calc 1 looks too crazy, so, you know, screw it. I'll just, you know, it could be one problem on the test, it could be maybe one problem on the final, right? But what I said before is constant behavior like that creates enough holes in your knowledge that when you reach a certain level in mathematics, you can't go past that level. If you accumulate enough of those, it's just, I really don't understand, and I don't have the time, or I don't have the will to deal with this one topic. You see, the entire problem that I did over here appeared yesterday in the problem in Calculus 2 as a little side calculation that was needed, which was maybe 2% of the entire problem. And that problem is listed actually in the textbook. I can find it in chapter 7. No, sorry, chapter 6. So I'm going to bring up that problem right now and show you. You will recognize the exact string. And it came up as a question because the student wasn't sure how to do the problem, because obviously the skills from this particular section were not there. So if you observe over here, the problem 29 has exactly the answer that you have in your notes now, right? And this integral is solved by what we call U substitution. You're going to learn that in this class. But there are some types of integration that you practice in Calc 2, and that integral shows there. Now, if you go and jump to the next page, the problem that I told you we're going to work on is somewhere over here. There it is, x raised to the tangent x. This problem appears over and over again in Calc 1 and Calc 2, and it goes down the line. So learning this technique is not just something that you need to survive for Calc 1, get the grade, move on, and if you can't figure it out, you know, then let's just skip it. Because this stuff is going to be there, and as you are building this math knowledge house, if you have enough holes, when you reach a certain level, it's not going to work. So the best advice I have is, when something is difficult, look at it, and fight to learn it, because that's exactly what separates you from those who are not learning it, right? It's the status of you're Calc 1 now, so deal with it, right? And then you're Calc 2, deal with it, right? And you are either there or you're going to join the other 90% that doesn't do it. That's how it goes. So here is the example for you. So y equals x raised to the tangent x. So now you know that you're supposed to ln both sides. Break it off. Let's go.
Yeah, we are using those rules to solve, but apply more to both sides and learn when you're solving equations for the first time. So when you have here, so
technically downward.
Oh yeah, that's it.
So since you have 1 over y, on the side, right? So 1 over y dy dx. You can multiply both sides by y to get rid of that, and then you just copy it over to the right side. Does that make sense?
solve this equation,
What is
you apply
y?
ln to both sides.
Y is that
ln
we already have
z,
one.
and you get x
It's
equals
x tangent, or x to the tangent x.
ln 9 you find them calculate.
So you
apply
always
log
copy
to
that
both
side over.
sides means
Don't even worry about
put in front of the make the entire expression. So make this the argument of the log you put in front. Make this the argument of the log if you put in front. You apply log to both sides, and then you do math calculation. You also have that trick. If you have, let's say, some questions, sine inverse of x is equal to, let's say, pi over 6. We will apply sine to both sides. Sine of sine. And then you guys cancel. X equals sine of pi over 6, which is a half. So when I say apply log to both sides, apply e to both sides, apply sine to both sides, that's what we. It's the same idea, like subtract 3 on both sides, except we do just add operation, not just additional divide both sides or multiply both sides. You multiply log, square both sides, with the square root, right? You do all the mathematical operations that already given to both sides.
So we're going to ln both sides and use the power rule to put the exponent down. So the rule I used was ln x to the p is p ln x. That was the rule. So that tangent x, the entire tangent x was p, and that drops down. So now when I have this, we differentiate and we get 1 over y dy dx is equal to, now we have a product rule, so copy the first. times derivative of the second plus copy the second, and derivative of the first is secant squared x. Exactly. So dy dx is equal to, the y goes to the other side, becomes x to the tangent x times tangent x over x plus ln x times secant squared x. There's really not much we can simplify. It's just what's there. So, where? It's under logarithmic differentiation in 3.9. That's yep. That's what we are doing now. 3.9. And I would like to pick up one or two exercises from the textbook. So all of the exercises that I did so far were the exercises which I made up. Here are two exercises from textbook. Let's do one of these that will be easier example, and then one that is a spicier example. So from the textbook, they're asking you to solve, this is problem 48. So find the derivative of the function y equals x squared plus 1 raised to power x. Mm-hmm.
So why is it always derivative of x over x?
So then I got like that word for like
What do you mean?
So you do this like so it would be say 2x over x squared plus 1, where based on that definition it would be 1 over x squared plus 1. It's 1 over x.
But that's the basic rule in the chain rule, right? This one. I over you.
How did that? What happened?
You prime over here, right?
All right, so this is again the same problem like above. Well, all of these are the same. You have ln both sides, so we get ln y is equal to x times ln of x squared plus 1. And now when we differentiate, we're done. 1 over y dy dx is equal to, on the other side we have a product rule, so copy the first times derivative of the second, so copy the function and its derivative on top, plus copy the second, and then times derivative of x, which is 1. So that was the product rule. And copy the function on the right hand side. This 1 over y goes as times y on the right, so that y is x squared plus 1 raised to the x times 2x squared over x squared plus 1 plus ln of x squared plus 1. And that's it. So it will take some time, right, to practice this. Obviously, you can't be experts in this tomorrow. You have to work on it. And depending on how far you push. So one more example. This is a little bit spicier version, right? This is problem 66. Y equals division line x to the 8 cosine cubed x divided by the square root of x minus 1. Let's see how that goes. Eight and then cosine cubed. So the first one is 8, the second one is 3. Exponent is half, right? It's a square root. It's a half exponent, and it goes in front of the ln. This minus becomes a minus because the derivative of cosine is negative sign. Usually when student says that, I say, of course, it's math. Takes some time to kick in, but once it kicks in, you always have it. Because it doesn't change. No, people change their opinions and stuff. Over here, this is it. It's been like this for thousands of years. That's it. And that's it for this lecture. I hope you're not disappointed. We're going to take a break, and then we'll do 310, the inverse of derivatives of inverse trig functions.